Great. We've now had an overview of our WALS matrix factorization estimator input function, starting from our TFRecord files, creating our sparse tensor features of rows for users and columns for items. But now, let's dive even deeper into the input function, starting with an examination of our custom decode example function. We've seen the overview of our TFRecord parsing function. Let's dive deeper into some of its components, namely the custom function, starting with the decode example function. We call our decode example using a dataset map, where x is our example protos, and our vocab size is either the number of items or users, depending on which phase of WALS we're in. We first want to specify the schema of the TFRecord files, using a features dictionary into either fixed length or variable length features. Let's say we were decoding the item TFRecord. Then the key will be the item index, which is just one value, therefore it is fixed length. The indices will be the user indices, and there are a variable number of these because some items might have very few ratings, while other items may have many ratings. Lastly, the values will be the ratings, which will be the same variable length as the indices. Using the feature map dictionary, we will now parse the features from the example protos, one example at a time. Now we want to use tf.sparseMerge to easily convert our indices and values into a sparse tensor, using the vocab size of the number of items or users depending on which phase WALS is in. Having the sparse tensor format representation of our data is a great choice since our matrix is extremely sparse due to a very high number of users and items. This way, using the vocab size, we only have to keep track of the interaction pairs that happened, and not all of the interaction pairs that didn't, through the indices tensor that corresponds with the values tensor that we set up when writing our TFRecords during pre-processing. Remember how we mentioned earlier that the batching process will replace, for instance, the item ID in the first dimension of the sparse tensor's indices with the index within the batch? Well, here we want to save the key into a tensor so that we can use it to remap the indices after batching is complete. Because this is a map, we are mapping the example protos in our dataset to sparse tensors, but we need some way to not lose our key so that we can fix the indices later, some place to store the key. A solution is to take the sparse tensor created by the sparse merge operation and create a new sparse tensor, but concatenate the key to the end of the indices tensor within. Because the indices and values tensors need to be of the same length, we also concatenate 0 to the end of the values tensor as a dummy placeholder. This way, the key is spliced into our mapping, which we can then extract later to fix the indexing. We are finally done designing our sparse tensor and return it to complete the dataset mapping operation. Now that we've gone through the decode example function, let's see what we have learned. In our decode example function, we use varlen feature indices and values of blank. We perform a sparse merge because of blank, and we concatenate the key because of blank. Choose the answer that best fills in the blanks. The correct answer is A. In our decode example function, we use varlen feature indices and values because of having many ratings per row column. For instance, when predicting items for users, each user will probably have a different number of items they have interacted with. The indices and corresponding ratings, the values. We perform a sparse merge because the WALS matrix factorization's input function needs the inputs to be sparse tensors. We concatenate the keys to the indices tensor because batching overwrites the first dimension of the indices with the batch index. So we use this trick in the remap keys function later to correct it.